Hi, welcome to the University of North Georgia online version of Math 3350 Probability and Statistics. This is our third segment, and we're going to look at some of the special counting patterns. Since the probability formula just requires us to count total outcomes, there are some patterns we need to know, and we went over some very important ones, the permutations and combinations before, but this lecture is going to talk about some different ones that are a little bit unique. They don't appear as often as the other types, but they're important to know about. They do occur. So permutations on a circle. So what about instead of arranging 8 people in a line, suppose we put them around a circular table? How many different seating arrangements are there? That's the first special pattern. The second one is the handshake problem. If 8 people attend a party and they each shake hands with every other person at the party, how many handshakes occurred? Unique arrangements. How many unique arrangements of the letters Mississippi are possible? So we've solved something like this, but when we did, all the letters were different. So if we had an 11-letter word, all the letters of which were different, this would just be 11 factorial. But we kind of are questioning ourselves, what is it when some of the letters or many of the letters repeat? And then multinomial coefficients, this will be an optional section, so no questions on tests or quizzes will include multinomial coefficients, but they are really, they do connect some of the important information in the course. So let's take the look at the first one. If 8 people go to a party, how many different ways can they be seated at a round table? Okay, well, one way to think about this is to build up from the bottom, right? What if we had 3 people seated at a round table? And you can actually draw that one out and see how many possibilities there are. And you can do it for 4 people, and you can find a pattern. And you should probably pause the video and take a moment to look at that. So here we have the situation with 6 people at a party, and I just wanted to show an animation of what's going on. So normally we would think of this as having 6 factorial permutations. If we were lining them up in order in 6 slots, A, B, C, D, E, F, if we had 6 slots, then there would be 6 factorial permutations. Okay? But when they're seated at a table, these folks seated at a table, some of the permutations are copies of each other, right? What if they all shift 1 seat to the right? Okay, now we have the exact same permutation. Nobody's moved. Everybody's sitting exactly by the same person they were sitting to. Everybody's sitting across from who they were sitting across from before. And here they've moved 2 seats to the right and 3 seats to the right. And you can see that they are still sitting across from the same person that they were sitting across from. A is still sitting across from D. B is still sitting across from E. C is still sitting to the left of B and to the right of D. Wait, has B on his or her left and D on his or her right. And so there are 6 possible different permutations that they can have. It just depends on which seat A sits in, right? A can sit in the first one, the second one, the third seat, and so on. So there are 6 different permutations. So we take our 6 factorial and divide by 6, which is actually equal to 5 factorial. So the number of permutations on a circle are going to be 1 fewer than the same number of objects could be permuted on a line. So back to the original question, how many different ways can 8 people be seated at a round table? Well, the answer is going to be 8 factorial divided by 8, or if you'd like, 7 factorial. Okay, what about the same 8 people at the party, but now before they eat dinner, they're all going to shake hands with everyone else? How many handshakes happen? Let's take a look at another animation. So the idea is that we're going to start with person A and have him or her shake hands with every other person. Okay, so there are 8 people, and the first person is going to shake hands with 7 other people. 1, 2, 3, 4, 5, 6, 7. Okay, so now A is shaking hands with everybody they can. Now we're going to look at person B, and they can shake hands with everybody except A, because that one we've already counted. So this will be 6 more handshakes from person B, shaking hands with C, D, E, F, G, and H. And then C will shake hands with 5 people, because he's already shaken hands with B and A. And then D will shake hands with 4. 1, 2, 3, 4. And then E will shake hands with 3. F will shake hands with 2 people. And the last one there is G shaking hands with the only person that he or she hasn't shaken hands with yet. So we have this pattern where we are adding up all the numbers between one and another number. So for the one that we had, we were adding up the numbers between 1 and 7. Okay, but before I try to figure that one out, this goes to the classic story of Gauss. And the story goes that a young boy, he's precocious at mathematics, and his tutor will give him a problem. He solves it so quickly that he's up getting another problem for the tutor to have to write down on his slate. He does that so quickly that the tutor doesn't have any time to do anything else. So finally the tutor gets frustrated and he says, add up all the numbers between 1 and 100. And young Carl Friedrich Gauss, little Freddie, says 5,050. And the tutor's like, how in the world did you get that? And so it's this same pattern. And what Gauss realized was that if you think of the beginnings and the end of this series, it's an arithmetic series, that you can pair up the values, right? If I pair up the 1 and the 100, they add up to 101. And if I pair up the 2 and the 99, 2 plus 99 is 101. I'm sorry, 1 and 100 is 101, 2 and 99 is 101, and so is 3 and 98 equal to 101. So there are 50 pairs of numbers that add up to 101, so 5,050. Okay, so going back to our problem, right, we know that we have 1 plus 7, that's 8. We have 2 plus 6, that's 8. We have 3 plus 5, that's 8. So we have 3 pairs of 8 plus half a pair of 8. So we have 3 times 8, which is 24, plus 4, which is 28. So the handshake pattern isn't used that often in probability. It comes up once in a blue moon, but it's such an important counting pattern. It's iconic. There's this story that lots of math teachers and math students know about Gauss. So this is important to learn about just for being an educated math person. And so remember that we're going to have this pattern where we add up the first and the last numbers and then multiply by the number of pairs, and sometimes it'll be half a pair. So I do have a little bit to sort out. And you can memorize a formula, but Gauss's idea is really important. So remember, this handshake pattern goes with Gauss's counting idea. So now the third one we want to talk about are how to do these unique arrangements of 11 letters when a lot of the letters are repeating, right? When I have repeated S's or other letters repeat. So we start with 11 factorial, right? We have 11 objects to permute, and 11 positions to rearrange them into. So how many possibilities are there? So let's get the iPad back out. And we got it woken up there. All right, so let's take a look at this. And so in the letters Mississippi, notice that we have 4 repeated letters. So we can start with 11 factorial in the numerator. But we're going to have to divide by 4 factorial. Why? Because once we arrange all 11 letters into some permutation, then there are these S's that we can't tell apart. And how many different patterns can the S's jump around into other S positions? Well, there's 4 factorial ways for those 4 letters to be permuted. And those patterns we can't tell apart. Notice that there are also 4 I's. There's an I, an I, an I, and an I. So I'm going to put down a 4 factorial for the I's because they can jump around into different I slots, and there are 4 factorial ways they can do it. Then the last one we have are the multiple p's. There's only 2 of them, so put in a 2 factorial for the p's. And so the answer is 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. Okay, so what about this example? We have college football players and the defensive team is being lined up. There are 10 players and they're going to be lined up into 10 positions. And the only way we can identify them is whether or not they are freshmen or sophomores or juniors or seniors. And we're asked how many different ways can they be arranged in a row. Well, this is interesting, but if you think about it, it's the same question we were just asked about with Mississippi. If all I can identify about them is their class, freshmen or sophomores or juniors or seniors, then I'm just being asked how many distinct permutations of the 10 letters exist. So this is going to be straightforward. Right? We're going to have 10 factorial in the numerator. And there was 1 freshman and 2 sophomores and 4 juniors and 3 seniors. Oops. So 10 factorial divided by, and 1 factorial is just 1, so 2 factorial times 4 factorial times 3 factorial. So here you see the solution. The 1 factorial has been left out in this particular version of the solution. So this is an interesting twist on the handshake problem. Now we're told that everyone is shaking hands with everyone else and the total number of handshakes is 66. What's the total number of people in the room? Well, we know there's more than 7 because 7 got us to 28 handshakes. But the best way to think about it is, hey, with 2 people, there's 1 handshake, and with 3 people, the first person shake hands with 2 others, and then the next person can shake hands with 1 other person, and we're done. So we do have this 1 plus 2 plus 3 pattern going on. And you can see that if we continue the pattern, a 3rd person is added on, and then a 4th person is added on that has to shake hands with everybody else. Excuse me, a 5th person, and they shake hands with 4 additional people. They don't shake hands with themselves. And we're told, hey, we're going to end up at 66. So what number of people were at the party? So there's a couple of different ways to solve this. It's a small enough number you can just continue the pattern. It turns out that the n that we're summing to is 11, right? So that there were 12 people at the party. Remember, n minus 1, different people. So let's take a look at the next example. There you go. If you sum up these values, if you sum up the values between 1 and 66, I mean, excuse me, between 1 and 11, you'll get 66. So this is the final thing we'll look at. This is the multinomial coefficient, or it can lead to the multinomial coefficient. And so what are the number of ways to take 10 people and place them in 2 groups of 4 and a group of 2 where order does not matter? All right, well, I've given you the whole setup. Let me highlight some things that are going on here. All right, so we're starting with 10 people, right? And we're going to get 2 groups of 4, but let's just start off with a group of 4. Well, how do I do that? Well, the first thing I do is 10 choose 4 right here, right? 10 choose 4 because I have 10 people and I'm choosing a 4-person group where order doesn't matter. Well, now after that, I have 6 people left. I need to get another group of 4. So here is my 6 choose 4. So I started with 10 and chose 4, then I had 6 left and I chose 4. Now I have 2 left, right? Now I'm doing the group of 2 over here. Doing the group of 2 over here. And that's my 2 choose 2. Now this just equals 1. So the only terms that are really doing anything for me are these 10 choose 4 and 6 choose 4. But I want you to notice what's going on, right? I have a term here that's canceling with the numerator of the next binomial coefficient, and then same thing, I have a term in the denominator that's going to cancel with the term in the numerator next to it. So this comes out to 10 factorial over 4 factorial times 4 factorial times 2 factorial. Okay, so in a moment we're going to learn that this is the multinomial coefficient, and the way I would write this multinomial coefficient is I would have 10 choose 4 comma 4 comma 2. So it looks like a binomial coefficient, but I'm supposed to list the groups in the denominator. Right? I have a group of 4 that I'm choosing, I have a group of 4 that I'm choosing, and a group of 2 that I'm choosing. So these numbers in the denominator have to add up to 10. Okay? And so it's a multinomial coefficient. Now we can do it this way. There's absolutely no problem with doing it the way we showed originally. And then this will help explain the pattern, right? Find the number of ways to take 20 objects and arrange them in groups of 5 at a time, where order does not matter. Okay, so if we return to the iPad, then let's take a look. Right, so we'll do the same thing. We will start with a group of 20, so we'll do 20 choose 5. Times 15, so we have 15 left, and from that group we'll choose 5, and then from the 10 that are left we'll choose 5, and then again we could do 5 choose 5. Sorry, I put in a division symbol that I didn't mean to there. So 10 choose 5, and then I could put in 5 choose 5, but remember 5 choose 5 is going to be equal to 1. So what is this equal to? The first one is 20 factorial over 5 factorial times 15 factorial. And then the next one is 15 factorial. See, we'll have ones that we can cancel in just a second, over 5 factorial times 10 factorial times 10 factorial over 5 factorial times 5 factorial. And as I was saying, we have a 15 factorial in the denominator and the next numerator over. And then we have this 10 factorial in the denominator and the next numerator over. So we end up with this final term. Sorry, this should have a factorial after it, sorry. So we end up with a 20 factorial. That's the only thing that hasn't canceled in the numerator. And then I have 4 groups of 5. So I have 4 5 factorials in the denominator. And this is the multinomial coefficient 20 choose 5 comma 5 comma 5 comma 5. So this brings us to the end of our session. Some special patterns that you need to take a look at. Again, the multinomial coefficient won't be required, but it is a quick way to take a number of objects and select unordered groups real quickly. And you can see their equivalents. That's what I was trying to show. But again, that's optional material at the end. So for the other 3 patterns, they will be required. Make sure that you read the text materials for the course and take the completion quiz. Good luck.